Well, hello again. Today we're going to investigate the properties of buffers. Buffers are special solutions that consist of a weak acid and a salt containing the conjugate base of that weak acid, and they have the magical property of being able to resist changes in pH, and they're super important in all sort of environmental and biological systems. And so this is a quick kind of demo to help you visualize kind of how they work. Here is our standard sort of setup with a couple of burettes, one containing hydrochloric acid, the other containing sodium hydroxide, and we're going to use those to sort of demonstrate what happens when a system experiences an input of either one of those materials, strong acids or strong bases. We're going to explore the properties then of deionized water, which is shown here in this large beaker, and I'm going to put a couple of drops of indicator solution in that deionized water so we can see the general condition in terms of acidity. The green color here indicating that the DI water is essentially neutral, having a pH close to 7. It's probably a little higher than 7, but you get the general idea here. And we're going to take then that deionized water and we're going to put it in two beakers. And then we're going to add to that beaker of deionized water first some hydrochloric acid and then some sodium hydroxide to the other beaker and see what happens. You remember our indicator solution will change colors at different pH conditions. So here then our first experiment showing the addition of, better turn on my little stirrer thing in there so that we can watch the solution stirring. 1 drop of hydrochloric acid, 2 drops of hydrochloric acid, 3 drops of hydrochloric acid, and I think you can easily see that the solution has gone red, which indicates the existence of acidic conditions, and that comes as no surprise because the water does not have any ability to absorb changes in the pH. Here, hydrochloric acid added to water produces hydronium ion, and that hydronium ion, you remember, is the thing that dictates the pH, and the pH then goes way down, indicating acidic conditions whenever we put a strong acid into water. We can try that same experiment, only this time using a strong base, sodium hydroxide. Same experimental setup, same starting pH, the green tint to the solution indicating essentially neutral conditions. And here as I start a very slow drip of sodium hydroxide into the beaker containing DI water, 3 drops, 4 drops, 5 drops, and you note how the solution has quickly turned purple, indicative of strongly basic conditions in that beaker, which again comes as no surprise because sodium hydroxide does not have, water does not have any ability to absorb sodium hydroxide. The chemical equation here showing you that the sodium hydroxide in water produces abundant hydroxide ions, and those hydroxide ions then give us our pH. The pH goes way up very quickly, indicative of a strongly basic solution. A very different situation exists when we have a buffer, and the buffer that we're going to use today consists of a solution of both carbonic acid and sodium carbonate. And if you look at the little drawing I've done there, it's meant to show you that the beaker consists of whole molecules of carbonic acid and the sodium hydrogen carbonate ions all mixed together. I've made this up ahead of time. This is what it looks like in the beaker, a transparent colorless solution. I'm going to transfer it into, before I do that, I'm going to add some indicator solution to see what our starting condition is. Here, that indicator solution then producing a kind of bluish green color, which tells us that the buffer solution is a little bit more basic than the deionized water, but still fairly close to neutral conditions. I'm then going to spread it out into our two test beakers, and we're going to repeat the experiment, starting as we did with hydrochloric acid and continuing with the sodium hydroxide. I'll turn that so you can see a little bit better. You can see the little stir bar in there stirring things up, and once again I'll start the burette, attempting to make it slowly drip hydrochloric acid in there. 1 drop, 2 drops, 3 drops, 4 drops, 5 drops, 6 drops, 7 drops, 8 drops, 9 drops, 10 drops, 11 drops. It just keeps coming, and as you can tell, the solution is really not changing color at all, suggestive of the fact that the pH is being maintained at approximately the same level as it was when we started. And the magic here is that the buffer, in this case the sodium hydrogen carbonate component of it, is neutralizing that hydrochloric acid by turning it into carbonic acid, which is a weak acid. And as a result of that neutralization or sequestering, the pH stays essentially the same as we continue to add that strong acid. And note that even now, after all of my yakety yak, the color is essentially the same as it was when we started. The buffer absorbing that strong acid and turning it into something that does not affect the pH. We'll turn that off, set that aside, bring up our second beaker of buffer, say that really fast, 10 times. Bring around our sodium hydroxide burette, and now start that experiment again with a slow drip. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and just like last time, the idea here is that because the color is not changing, we infer that the pH also is staying relatively the same as it was when we started. That bluish greenish color then suggestive of a relatively neutral pH. And in this instance, it is the carbonic acid component of the buffer that is neutralizing the hydroxide ion, making water in a classic neutralization reaction, and releasing the sodium and hydrogen carbonate ions, so that after a continuous addition of that strong base, the pH essentially staying the same. And that's the hallmark then of all of these buffer solutions. Here the beaker containing the buffer and the sodium hydroxide, here the beaker containing the buffer and the hydrochloric acid. Note that they are essentially the same color, indicative of the fact that the addition of acid or base didn't really change the pH, compared to our deionized water control beakers, where the addition of acid produced an immediate decrease in the pH, and the addition of sodium hydroxide produced an immediate increase in the pH, both of which would be presumably lethal to some organism. But buffers have the ability then to absorb and regulate that pH, and as a result perform an amazing role in terms of the maintenance of homeostasis in larger organisms. Pretty cool, huh?